All right, let's jump right into this. Imagine, just for a second, that you actually possessed a piece of technology capable of looking billions of years into the past. And I'm not talking about some wild concept from a sci-fi novel, but a very real, physical time machine that's hovering out there in the incredibly dark, freezing expanse of space right now. Welcome to this explainer on the James Webb Space Telescope, or JWST. Built through this absolutely massive collaboration between NASA, the European Space Agency, and the Canadian Space Agency, I need you to know this isn't just a piece of equipment for taking pretty pictures of stars. It's a phenomenally advanced instrument designed with one ultimate goal: to witness the literal dawn of the universe. So what if you could actually look 13 billion years into the past? Because the James Webb Space Telescope was engineered to do exactly that. Its entire mission is to capture light from the very first stars and galaxies that formed mere millions of years after the Big Bang. We are talking about peering straight into the cosmic dawn, capturing the literal origins of everything we know. But you're probably wondering, how is that actually possible? How can a bunch of mirrors and sensors look backward in time? Well, to wrap our heads around how that works, we gotta start with a really simple number: 8. The absolutely crucial thing to remember here is that light, as incredibly fast as it is, still takes time to travel across the vast emptiness of space. Think about it. When you walk outside and feel the warmth of the sun on your face, that sunlight hitting your skin didn't get there instantly. It took approximately 8 minutes to travel from the sun all the way to the Earth. That means you are never actually seeing the sun as it is right this very second. You are seeing the sun exactly as it was 8 minutes ago. You are, quite literally, looking 8 minutes into the past. Okay, now let's scale this up, like way up, to a cosmic level. 1,000,000. If we take a telescope and point it at a star that is 1,000,000 light years away, the light hitting our lens has literally been traveling through deep space for 1,000,000 years. That means we aren't seeing that star as it exists today, not at all. We are seeing a snapshot of it exactly as it looked 1,000,000 years ago. So the rule here is simple. Looking deeper into space is fundamentally identical to looking deeper into history. And since our universe is roughly 13.8 billion years old, building a telescope powerful enough to see things 13 billion light years away means we can effectively watch the universe's infancy unfold right before our eyes. Now, older instruments like the incredibly famous Hubble Space Telescope have given us some breathtaking views, mostly using visible light. The exact same kind of light our human eyes can see. But visible light has a massive glaring limitation. Space is wildly dusty. Giant, thick clouds of cosmic dust and gas completely block visible light, hiding those super early galaxies that we desperately want to see. And this is exactly where JWST completely changes the game. JWST doesn't rely primarily on visible light at all. It relies on infrared light. Because infrared has a longer wavelength, it can effortlessly pierce straight through those massive clouds of space dust. It's kind of like how your home's Wi-Fi signal can easily pass right through solid walls. Infrared light works in a really similar way through cosmic dust, allowing JWST to reveal a totally hidden universe that was previously entirely invisible to us. But wait, there's another absolutely foundational reason why infrared is a total necessity here. It's a wild phenomenon called redshift. See, ever since the Big Bang, our universe has been constantly expanding. And because the actual fabric of space itself is stretching out, the light traveling through it from those distant, ancient galaxies gets stretched out too. As that light wave stretches over billions of years, its wavelength becomes physically longer. It shifts completely out of the visible light spectrum and gets pulled deep into the infrared spectrum. So if we want to see the oldest, most ancient light in the universe, we absolutely have to look in the infrared. That ancient light has quite literally been stretched into the infrared spectrum by the expansion of the universe itself. You've definitely seen pictures of JWST's iconic honeycomb-shaped mirrors, and you've probably noticed their brilliant, shiny golden color. Well, that isn't just some fancy gold paint. It is a microscopic coating of actual, literal 24-karat gold. And no, this isn't some extravagant luxury just to make the telescope look cool for the cameras. In the realm of physics, gold is scientifically the absolute best material in existence for reflecting infrared light. The sheer, enormous size of the mirror allows it to capture as much of this incredibly faint, ancient light as possible, while that 24-karat gold ensures that nearly 100% of that infrared light is perfectly bounced right into the telescope's super-sensitive sensors. But capturing infrared light comes with a massive catch, a terrifying vulnerability, actually: heat. You see, heat itself generates infrared light. Even you and I are glowing in infrared right now. If the James Webb Space Telescope were to get even slightly warm, the infrared heat radiating from its very own machinery would completely blind its sensitive sensors, totally ruining the deep space images. To prevent this, the telescope must operate at an unimaginably freezing temperature. We're talking minus 223 degrees Celsius. This deep freeze is absolutely critical. It ensures the telescope itself is thermally silent, so it doesn't accidentally drown out the whisper-quiet infrared signals coming all the way from the edge of the universe. So how do you pull that off? How do you keep something that freezing cold while the sun is blasting it? You build the ultimate sun shield. This thing is roughly the size of a full tennis court. It's made of a highly specialized material called Kapton, and it utilizes 5 distinct, incredibly delicate defensive layers. Get this, each one of those layers is thinner than a single human hair. But this 5-layer system is unbelievably effective at blocking the sun's heat. It creates a permanent freezing shadow where the golden mirrors and sensors can operate safely, even while the telescope is floating out in space, constantly getting bombarded by the blazing heat of the sun. But here's the thing. Even with that epic ultimate sun shield, the telescope still couldn't just hang out in low Earth orbit like Hubble does. Our Earth actually reflects a massive amount of heat and light from the sun, and being that close to our warm planet would totally ruin JWST's instruments. So to stay perfectly, permanently cold, the telescope had to be sent away, far, far away, a staggering 1.5 million kilometers out into deep space. And it didn't just get shot out into a random, empty patch of space either. It was sent to a highly specific gravitational sweet spot called the L2 point, or the second Lagrange point. At the L2 point, the gravitational pulls of both the sun and the Earth balance out absolutely perfectly with the orbital motion of the spacecraft. It is this brilliantly elegant physical balancing act that allows the telescope to literally hover in place, permanently positioned in lockstep right behind the Earth. By chilling at L2, JWST keeps the sun, the Earth, and the Moon entirely on one side of its sun shield, ensuring its incredibly sensitive mirrors remain in permanent, freezing darkness. Now, think about the pressure here. Getting a $10 billion, wildly complex machine out to that point, a million miles away, came with astronomical stakes. When the telescope launched, it was completely folded up tight to fit inside the rocket, which meant it had to unfold and assemble itself entirely on its own out in the void of space. NASA identified over 300 single points of failure during this deployment sequence. 300! That meant if just one motor got stuck, if just one tiny cable snagged, or if just one of those incredibly thin sunshield layers ripped, there was literally no backup plan. There's no way to send astronauts 1.5 million kilometers out to fix it. Just one tiny mistake out of 300 possibilities would have instantly destroyed a $10 billion mission and decades of human effort. Talk about a nail-biter. But thankfully, the engineering was completely flawless. To really cement just how profound this telescope's view of the universe actually is, I want to share a totally mind-bending thought experiment with you. I love this one. It's called the dinosaur paradox. We know that looking into space is looking back in time, right? So, imagine for a second that there is intelligent alien life sitting on a planet exactly 65 million light-years away from us. If they were to point their own version of the James Webb Space Telescope directly at Earth, right this very second, the light they would be capturing in their lenses is 65 million years old. They wouldn't see our modern cities or our oceans as they are today. The light reaching them right now would show them an Earth entirely ruled by dinosaurs. That is the true, staggering power of a cosmic time machine. The James Webb Space Telescope is just so much more than a telescope. It really is a mirror reflecting our cosmic origins, showing us exactly how the very first galaxies spun into existence, and maybe even giving us crucial clues as to how life itself began. It has successfully pierced through the veil of cosmic dust to show us the universe's incredible hidden history. Which leaves us with one incredibly powerful, lingering question to wrap up this explainer. If you had the remote control to a perfect time machine, would you choose to look deep into the past, or would you want to look far into the future? Think about it. Thanks so much for joining me on this incredible journey through space and time.